So here is a video on YouTube all about color profiling. So I wanted to show you how to use your Munsell color chart. Let's see here. It should be playing.
For soil color, what I'm going to do is pull a new sample and I'm going to insert my knife into the soil profile, pop it out, and I'm going to break open the PED to get a fresh piece that doesn't have any dried soil on it or any smeared soil from my knife. I'm looking for that fresh piece. Now if the soil was totally dry, I could mist it with water from my water bottle because we like to do moist colors. But you can also do dry colors. You just want to record on your data sheet what you collected, dry or moist. So this soil sample is plenty moist as it is, so I'm just going to use it like it is without adding any moisture. I'm going to grab the Munsell soil color chart, and a very important trick to using the Munsell soil color chart, and I would say not trick but really a rule, is that you have to have your back to the sun. And also, you're not supposed to wear sunglasses. You're supposed to do this with your naked eyes. I'm going to flip around here.
So some of the reasons why you want to do it with your naked eyes is because you want to have you don't want to have that color influenced by the lenses. So one of the things that I do when I do field work and we talk about soils and we do the soils thing is we always record what the weather is like, because if it's sunny or cloudy out, it'll vary how you see color. Also, as she said, you're putting your back to it, and so you're looking at it in full sun, but sometimes it's cloudy, or we've done soil judging when it was raining out, and so you got to do the best you can.
Put the sunglasses back. We're shooting this in Kansas, and so a good starting point for many of our, upland soils would be to start with the 10YR page. That is because it's got some dark colors on it that are usually a good starting point.
So 10YR is also a really good starting point for the state of Illinois. We have the same kind of dark soils inside of here. If you ever get a Munsell color chart book from our like the geology or geography thing departments, you'll have certain pages that are just completely just covered in soil because they've been used so much, because it's just the normal soil colors around here.
If I was in southeastern U.S., I'd start farther towards the front of this book on the redder soil color pages. I'm going to take the PED, and all I'm trying to do is match it up with the appropriate soil color chip. So for example, this particular piece of soil looks like it matches fairly nicely with the 10YR 3-3 chip, which means that it's dark brown in color.
So if I go back here to my lecture, okay, so this is what the page of the book looks like. So she was talking about 10YR. This is the 7YR. So that's just the name of the page. So Munsell came up with a way to give a number to it so that you could pinpoint which one. You can actually give these colored, the 7YR 6-3 to a paint shop, and they'll give you that color. I mean, this is the same colors that they use for paints and stuff. But, you'd match up your color to it, and then this tells you, like, these colors here are brown, these are light brown. These are the names that we give these colors, but we generally give them by the number. So we look at the 7YR, just tells us what page we are on. Then we get the value. So which value do we use, and then which one is the chroma on this side over here. Now, let me see if I can open it. I'm going to pause you for a second. So if you go on, like on my cell phone here, I have a thing called Munsell Viewer, and it's an app that you can use to soil color and stuff like that. And so you can use display, you can click on it, and you can get your different color hues on here and stuff, and you can compare and contrast your colors to, so I'm going to use a YR, I'm going to use this 7.5, so there's the 7.5 YR on here, and it gives me the color and stuff like that. And so there's apps out there where you can use your phone too to do the color matching. The books are quite nice because then you can actually hold it up and then in the field and stuff. But color, this is one of the things we use, and it tells us a lot about the soil just from the color. So one of the things that she mentioned in there was we took it out of the soil profile or soil horizon. Well, one of the things that unless you start looking, you'll never realize that soil has these what we call horizons. They have these layers in them that are they're not located in every soil. Like I said, every soil is unique. It's based upon all of these other parameters, how they get created and how much time it takes. But what we have are these very distinctive colors that come through, and we can see these horizons. We call them horizons. We don't call them layers. We call them horizons. And so we have these different horizons that happen here. I'm going to start at the bottom instead of starting at the top, because the bottom is either bedrock, so hard bedrock, we call that an R horizon. So if you go down deep enough, and you'll hit the the rock or the bedrock. Now, if you notice, there's no depth on here. There's no like, oh, you look at the first 10 inches or the first 3 feet or the first whatever. Different soils will have different depths based upon where you are. I've been to some places where they've got inches of soil and places where you've got 3 to 6 feet of soil. And so it depends, and you might not even have bedrock, so the R horizon might not be in our area. Now, we've talked about, and you're looking up for on Illwater, you're getting to see all those different horizons that are inside of there, and you're seeing how deep it goes down into the soil until you hit bedrock. So sometimes the bedrock is not near the surface. Then we have what's called the C horizon. The C horizon's right here, and this is partially weathered parent material or partially rock fragments of different size. So the parent material is what was originally there and got weathered with a lot of time. And so this is the original material. It might be partially weathered, so because it's not the rock that was broken up, or it was in our area, because remember we talked about loess. This could have been the loess that was laid down inside of there, and so we can get this parent material down lower. Then we move up to the B horizon. The B horizon is the zone of accumulation of fine materials and mineral precipitants. Okay, so the B horizon, we also refer to this as the subsoil. So this is the soil that if you dig down through that black soil, you would hit this major part of your soils, usually the B horizon. Well, the B horizon here is the zone of accumulation. That's the important part of the B horizon. It's the zone of accumulation. Well, where is it accumulating from? Well, as there's rain happening at the surface up here and it slowly moves things through the soil, it'll accumulate in the B horizon. Okay, so it's clays. So as water goes through here, it'll dislodge little clay pieces and they'll accumulate in this one. Carbonates. So we've talked about carbonates, calcium carbonate, limestone, all like that. Well, we have rainwater is naturally acidic. So as rainwater is slightly acidic, it'll dissolve some of that and it'll move and it'll accumulate in this area. We need accumulation of iron a lot of time, gypsum. So this is the zone of accumulation. So that's our B horizon. Our A horizon is the leached material horizon, black in color, which contains a high content of organic material. This is our topsoil. So our A horizon is our topsoil. So this is what we, you could buy a bag of topsoil. You're just buying someone else's, soil. But this A horizon here is leached. So what does leached mean? It means that as the water was going through, it's leaching out a lot of these materials that accumulate in the darker color in the B horizon, and they have a high content of organic material. So higher content. So this is the A horizon is what we see around here. It's our organic. It's got a lot of humus, not hummus. It's humus in it. So it's our black soils that we have at the top. So it's the A horizon here is our topsoil. Our O horizon is usually right where the plant leaves are. It's undecomposed materials. It's usually the O horizons, like if you dig in your backyard, it's like where the grass roots are, or it's right at the top where the dead leaves are and they're all accumulating and stuff like that. That forms the O horizon. You take a shovelful and you get down, you're going to immediately get into this A horizon where all the organic material is. And as we talked about with color, The A horizon over here is what you're seeing here. You're seeing this A horizon here having lots and lots of dark black color, poorly drained soils, but this is where all that organic material accumulates. While here, the A horizon is lighter, and it's not black, but it's still a darker brown color inside of it. And then their B horizon's right here. So you can start to see these layers forming in there. And so you'll have this O horizon at the top, which is the organic material, the humus inside of there. And then we'll go down to the A, B, C, and then R. And that's how we usually label them. Okay. So soil profile, so these are the horizons, or what forms across it this way. A soil profile is the whole thing that you see here. The soil profiles where we dig in, we always use something for scale, so here's a shovel for scale. What we're looking at is this whole profile of like this together. What kind of soil is this all together? This tells us a story. We have our bottom horizon down here, our R, or probably our C horizon. We've got our A horizon up here. This is probably an E. We don't have an E listed on these. Yeah. But this could be a different soil horizon in here, and then we could get into R, into there. And so we've got these very distinct layers that happen into it. And so this profile here, the soil profile, and what do you see? Well, you see these colors. You see the organic material at the surface. You see iron oxides forming in here. So that's where the water is drained out. And so this is a zone of accumulation right here. We see that this is well drained. You can see little like roots going here, burrow holes and stuff like that. And then the horizons are the different layers that form inside of it. And then, so we see different colors and textures. So there could be sand, silt, and clays inside of these. And then they form from the top down. So these soils, this all would have been one type of material, and then the glaciers left. And then we had all of those thousands of years for the soil to be formed inside of that loess that was left behind after the glaciers. And so we have different soil names and horizons. So we give names to soils. So one of the things that happens is that when we look at the different horizons that are in here, and then we come up with a soil profile, we'll come up with a name for it. So in this case here, we can get this really black soil here. So this is the A horizon. These lower cases here, those are subsoil types. So what'll happen is they'll mean different things. So the AP horizon stands for the plowed of the A horizon. So if you get a lowercase b onto there, it stands for a buried horizon in there. So you can get these A horizons in there forming in different ways. So and here, so we have this AP, so this is plowed, and it's very typical. It's about the top 10 inches. That's usually our upper part where the plow goes into it. And so this is the whole A horizon here. This is the whole A horizon. Notice they're different depths. They're different thicknesses. Not all soils have the A horizon goes down 20 centimeters. It really varies from soil to soil because of like all those parameters I mentioned before. And then there's the B horizon. This is the zone of accumulation, and then our parent material down here. Our two main soil types in the state of Illinois. So these are our names of our soils. Here's our different horizons, and then our soil profile. And we have names for them. So we have what are called mollisols and alphasols, are our main soils in the state of Illinois. Alphasols are those lighter brown colored soils that you see around here, and mollisols are those ones with the deep black colored soils at the top. And so it's very easy to see, like if you're driving around, you'll see alphasols and mollisols around the area. And if we look at this slide here, it gives us the main types of soils across the country. And so these are all the different soils. And you notice that, like, as she said in that video where she was talking about Kansas, and if she was down in the southeast, she'd be more into these kind of things. You can get into inceptisols down there, which are, I was over here in East Tennessee, we would have inceptisols, which are just really old soils that have just been really weathered. Here in the state of Illinois, we're just really with alphasols and with mollisols. And one of the things that if you look at the word alphasol, it stands for aluminum, so Al. alpha, the Fe, it's Fe, normally iron, but this stands for iron, and Sol's is soil. So this is a soil that has a lot of aluminum and iron into it. That's where the name comes from. Sol means soil. So you can have a paleosol. A paleosol would refer to an old soil, a buried soil, a soil that was historically older. So when we talked about glaciers, we mentioned about the Sangamon soil. And if it's buried, that would be a buried soil, or a paleosol that was buried because of the last glaciation. It was buried. It was the Sangamon soil formed inside of the Wisconsin age. The Illinoisan age materials. And so when we go back to this slide here, we can see this. So make sure you read all about the state soil. Make sure you read up about it and understand where our state soil comes from and where that is at. So what is soil usually made out of? Well, soil is made out of pore spaces and solids. So we mentioned the vadosome, remember the word vadosome? So the vadosomes, a lot of times, unless it's completely saturated at the surface or above the surface where you get wetlands, you usually have a mixture of things. So you'll get pore space and you'll get solids. Of the pore space, you'll have air and water in the vadosome. If it's completely saturated, you're below the water table, but usually you'll have air and water. And then you'll have the mineral part of the solids, so the inorganic part of it, and then 5% of it is organic. So the organic matter comes from the plants and animals and stuff like that. But this is kind of your average soil that we would have in our area here. Well, one of the other things that we look at when it comes to soil is the soil texture. So what does soil texture mean? Well, the soil texture is referring to the amount of sand, silt, and clay. So when we say sand, silt, and clay, we are referring to a size particle. We are not referring to a mineralogy of something. And so we go with these different size particles as referring to the percent sand, silt, and clay. So when we look at sand, sand particles are between 0.5 millimeters and 2 millimeters. That's the definition of a sand. So it doesn't matter what the mineralogy is. If it's in that grain size, it's a sand. Okay. You can get into quartz sand. You can get sand made out of almost any material, but we're going by a size here, not by a mineralogy. Silt. Again, silts are formed with the loess. Remember that? We talked about it. But what is silt? Silt is a size particle. It's 0.002 millimeters to 0.5 millimeters, so it's a lot smaller. It's in the middle. And then clay is anything that's less than 0.002 millimeters. Well, sometimes it's hard to tell the difference between these two. And so one of the things we used to do when we used to do soil judging is we would use our left hand, and you would learn how to, you would practice feeling the texture of the soil. So you would get used to taking your fingers and rubbing them together and going, okay, how sticky is it? How gritty does it feel? To figure out what the percent of sand, silt, and clay was just by feeling it. And so one of my exams I had in a soils class was what the exam was little buckets of soil, and we had to go around and say how much percent of sand, silt, and clay was inside of it, just based upon feel. And we usually use our left hand, so our right hand was clean to write notes. So we would get into percent sand, silt, and clay. But the other thing we used to do is you could taste it. If you can't tell the difference between silt and clay, if you put it into your mouth, clay tastes creamy or is creamy in there. Silt is gritty, because you get silt in your mouth, it's got that little grit inside of it in there. Okay, so we have sand, silt, and clay particles. Well, we have what's called the texture triangle. So this is the texture triangle, because not everything is just sand, silt, and clay. It's a combination of those three components into our soil. So say we have something that is 23% clay, 35% sand, and 42% silt. So what we look at here is this is silt from 0% silt to 100% silt. Down here is sand from 0% sand to 100% sand. And then on this one is clay from 0 to 100% clay. So if we took those ratios and we line up the three components, we would end up with what's called a loam. A loam is a mixture between the three of them. If you have almost 100% silt, over here you would have, that would be in the silt, over here in the sand, and here's the clay. But then we have different combinations of it here, like here's a silty loam, a sandy loam, a loamy sand, a sandy clay loam, a sandy clay loam, a silt clay loam, and then a silty clay. And so what we do is we look at the percentage of them and we give them classifications. Well, this becomes really important for water movement, for contamination movement, how plants grow inside of it. So by knowing the percent sand, silt, and clay, we can tell a lot about the environmental issues that are going into how well can you put in a septic system? Is this well drained? So you'd like to get something that doesn't move too fast, so you don't want to put it in sand because you want some treatment. So you want sandy loam, silty loams in there are great, especially a loam is great for putting in a septic system. And so when we look at soils, we also look at how much water do they hold. Because if we're in sand, if we get, this is inches of water per foot of soil, they drain really fast. So what we do is this is available water for plants. If we have less water than this, it's the wilting point of plants. If it's the field capacity, meaning that it's completely saturated. And so the water becomes almost unavailable, becomes anaerobic, all that stuff we talked about before. So when water is on the soils, we get what's called this water that's really bound so tightly to soil that it's not available for plants. A plant root can't to extract it. And there's a whole class called soil physics. And we go really in depth into, we can even go this into the hydro classes where we go really in depth to the physical reasons why that water is really bound tightly to the soil particles. And then we can get into capillary water, and this is where plants love it. A little bit of air, the water's moving and stuff. And then once we reach field capacity, that means it's completely saturated. Then we start to see water, the water moving out of the system, and then we're reaching what's called field capacity. And so this is where the water is available, and it depends on the texture of the soil, where that water is available. Notice like the silty loams and stuff like that, it's got the most water availability. It holds a lot of water. It's got that real nice right in the middle there. But clay versus sand and how much they have into their impacts, how much water they can hold, and when the wilting point of the plants will be. The other thing that happens with soils is soil structure. So the structure of the soil is a combination of the arrangement of the primary soil particles and the secondary units. So we can get things that a soil looks granular, it can look platy, there can be prismatic or columns, it could be massive. You can get these little wedges forming into there, you can form these sublinears. And this is where we get soils forming aggregates. They form stable aggregates, or we call them PEDs. So when you kind of break apart the soil and you watched her break apart the soil just kind of naturally, it'll form these different aggregates together. So it's a structure of the soil that comes apart when we start to look at it and we start to break it apart, and it'll just naturally form these clods into there. So compare this to the clods, which are caused by disturbances. So we get these clods forming by plowing or digging. So we'll get clods forming in there in the plowed part, while we'll get stable aggregates or PEDs forming deeper down. And then we'll also get compaction forming in these soils as a result of traffic. You break down these stable soil particles right in here, and you get it just constantly being driven over by farm equipment or by a road. You're going to get this compaction happening, and you're going to break apart these natural soil structures. And these soil structures are really important for water movement that goes into here. Can you see how with the pollution, the D naples and L naples would be influenced by all of this? What type of microorganisms would be in here is all influenced by the soil structure. And this is what a granular would look like versus a blocky soil would there. And you learn how to name these in the soils because of their natural things. And they tell us a lot about the movement and materials of the soil. And so a lot of the soils around here, we will have, like at the top, we'll have it be granular, and then you'll get this E horizon. We didn't talk about the E horizon. Don't worry about the E horizon. If you go to the UP, you'll find the E horizon up there. Like I was really excited. We were driving around. I'm like, stop the car. I got out and I'm like looking at an E horizon because I was all excited. We're not going to talk about it in here, but you can get platy material in there, and then you get into the B horizon. It could be blocky, and then the C horizons are generally massive, but they don't have to be. They could form other things, but you can get these different soil textures happening also with inside of your soil. These soil structures happening inside of there. So bulk density is another parameter that we look at for soils. And then we can quantify. So we just talked about that soil is made out of the mineral fraction and the pore fraction. The pore fraction is made out of water and air. And so soil is made out of that. And so we can do the ratio between the weight of the soil versus the volume of the soil. So the volume is like the size. So if we took a 1 inch or 1 centimeter cubed of soil and we weigh it and we do it how many grams that weighs per volume, we get the bulk density of the material. And so we do that ratio. It's expressed in grams per centimeter cubed. And soils will change as they become more compact, because now we're getting rid of that pore space and we're putting into that same volume, that same 1 little centimeter cube, we're putting more and more soils. So like concrete or things that are really highly compacted will have a very high bulk density, while uncultivated soils, those soils that you find in that light fluffy soils that you find inside of forests and stuff, that will have a very low bulk density. So there's a lot of air into it that allows for microorganisms and plants and everything to live inside of it. And so we can get these different bulk densities, and it tells us how much pore space we have versus how much solid materials we have. So we use bulk density a lot. And bulk density increases with depth just because you have that weight of the soil on top of it, and so it'll increase with that, and also with compaction. Roads, traffic, agricultural equipment will increase the bulk densities of the materials. And so you can get different bulk densities of different soils, and this is just showing us like if it's cropped versus uncropped of the same soil. Once we put crops in, we change that bulk density versus in the same exact soil in the exact same location, just not in crops, it's just never been in crops, will have a totally different bulk density. Because we compact things when we farm, we're driving over it, we change that soil structure and that amount of soil that it can have into there. So soil, the structure that we just talked about, the density that we just talked about and everything. And as I mentioned before, how do soils form? Well, they're influenced by the water movement through it. So the climate, how rainy is it? How well drained is the area in there? How much water gets retained? So the zone of accumulations, how much water, like if you've got a lot of clay, you might get a lot of water retaining into there, which will change the redox conditions, the soil temperatures. So we'll have different soils here versus in the southeastern part of the United States due to the soil temperature. Gas exchange, so gases are formed inside of our soil. So we can get CO2 forming inside of the soils because we've got microorganisms inside of there. We can get gas exchanges. I mentioned anaerobic conditions. If it's completely saturated, you should know all that already. The erosion potential, so where it's located on the landscape. And then how much fertility. So lands, animals, and stuff like that live inside of it. And so the hydrologic cycle, as you would mention, I would mention it, and soil properties that are part of the hydrologic cycle. So really the bulk density, the texture, the structure is really impacting how water moves through the soil, what color it has, the temperature influences, and we'll talk about pH, impact the soil horizons and depth. So that is it for today.